I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. We thank you for the weekend. Thank you that I'm not sick. Help us to stay well and just understand more about this A calculus. And be with Khang today. Help him to have words to explain what it is we have on the board here. In your name I pray. Amen. So I'll let you take over. So what are A and B?
A and B is algebra, associative algebra over a real or complex field. Okay. So first thing I want to talk is there is a submotivity constant. That, like for an algebra, something like the smallest real number such that you have a product rule, right? It's not nearly a product rule, but it's like sub-multiplicative rule. So I just define MA to be the infimum of that.
Oh, okay.
Rather, it's a minimum because we can achieve the minimum of it.
Yeah.
Just by taking the equivalent one as.
Certainly, one current ambiguity in my writing is I sometimes know I don't work with the unique, like the infim.
Yeah.
I'll just work with an m sub a, which works. But
yeah.
So you're trying to explain how to find like the best.
Yeah, the best one.
Yeah, the sharpest
and
one.
I try to explain also that the best one can be achieved at some points, like mathematically.
Okay.
So it's just about infimum on the like a sphere thing. A sphere thing. So it's compact, and so we got the infimum as a minimum of it. So if B is the isomorphism of algebra, and we have a norm on each algebra such that we have this equality, then I can prove that there's some multiplicative constant can be related in certain way. So this is the proof. You got phi xy equal to kxy, and then less than or equal to ma times x times y, which is the definition of ma. Yeah, the definition of ma, because xy is in a. And then we translate back to the phi one. So we got this ma over k times phi x times phi I. So by the definition of mb as the smallest one, we got this inequality. And the next thing we do is to do it on a instead. So we got kxy equal to phi xy, like the definition of this one, and then equal to phi x times phi I, because it's algebra homomorphism, and then less than or equal to mb times phi x times phi I, and then less than equal to k squared mb times x times y. And again, we got ma as the smallest constant, so that we have inequality of xy less than or equal to ma times x times y. So we got ma less than or equal to k mb. So from this inequality, we can conclude that ma equals to k mb. So they relate by a constant k. That is like a dilation constant.
So this is it somehow reminds me of these. We sometimes do something when you have three norms and like the arguments when the norms are related, and this is it's not that argument, but
I think it can work for
neat
general. But
so this just shows.
So we have this result here.
Okay, and so this is where so the first order of business to say something concrete is to remove my ambiguity about using any m sub a. You have to pick the inf, which picks out a specific m sub a.
Yeah.
Uniquely so.
Yep.
And then you can go from there.
Yeah. I just abused the definition as the smallest.
I think that's what I think my definition should be replaced with your definition. That's a better definition, really,
I guess.
for m sub a.
but it's kind of like hard to find it in practical application. Like I tried one, but okay.
So is the k just, you don't know what the k is, it's just a constant?
Yeah, and the norm must have some properties so that like they have
So that you can,
yeah, they can turn into a dilation. I mean, the isomorphism of algebra can turn into a dilation.
okay.
Yeah. So we got to the Rm times Cn case one with a little bit of modified norm that I think is called a weighted Euclidean norm. So I mean, you just have the constant Ai and Bj here. I forgot to mention, but it's all larger than 0. So in this case, I can prove that, but it's such a hurdle to like write all on the board. So the submultiplicative constant of this half norm should be square root of the minimum of all A and Bj. So I get an example here so that the next.
So typically,
Yeah.
typically we work with just the regular Euclidean norms
Yeah.
in Rm and Rc.
Yeah.
So in that context, the A's and the B's are all 1.
Yeah. Yeah. The normal Euclidean norm will have a submultiplicative constant 1.
So yeah, right. So
Yeah.
okay.
I mean, this you can just prove that the the inequality, and then you find a point where they can achieve the minimum. So it's right. I think it's the technique to do. So I just mentioned an example here because I will use it for the next application. So there's a modify. The real part is just normal real one, but the complex part has the 2 constant. So the next one will be isomorphism between the hyperbolic number and the direct part. So I just write these things out so that is somehow. It's just the writing, but I will explain that why do we have some kind of monstrous thing here. So we got a decomposition, representation. Just a Chinese remainder theorem thing. So I just factorize this thing into x minus 1, x plus 1, and this quadratic polynomial comes from the 2 roots of I e to the I k pi over n and e to the I minus k pi over n.
And what's K?
K
K
is
is
just a constant, like running from 1 to
yeah, K
n.
is true.
Yeah,
It's not. N is a fixed dimension thing here.
So this isomorphism is particularly applied for 2n, but the 2n plus 1, the odd one, is a little bit different, but it's still the same as the factorization of the polynomial. So using this, I can infer that this polynomial will be transferred, like it's just like replacing x to j here. So when I using the Chinese remainder theorem to each component of this factor, I will get the same polynomial, but just replacing the rule, right? X equal to 1 here, so I just replacing x equal to 1, and I get the first one, and x minus 1, and then I got the second part. And for this part, I will replace x by e to the I k pi over n. So it explains why. I left this one wrong. So it explains why there's this part and those parts.
Huh.
So I just substitute x as e to the I k pi over n. So I got the first one, and then e to the I pi over n. So I got the first one, and then this is a e pi I over n. The second one will be e to the 2 pi n, and the last one will be e n minus 1 pi over n.
Huh. For the n minus 1 component, n minus 1 complex components.
Yeah. So using the norm that I mentioned before, I can prove that A0, the standard norm on the hyperbolic number times n will be the weighted Euclidean norm on this enormous topple real and complex number. It's a very long to simplification, but certainly that I do it like I checked already. So.
Huh. Yeah, I'm trying to make sure I understand the isomorphism. Sorry.
I can this is 2n, so I can get it to x2 first.
Yeah, can you show us this? Can you show us the isomorphism explicitly for like n equals to 2?
Oh.
That may be a good starting point.
Yeah, I intend to do it for x2 so that
Oh, okay.
it's more clear. So
You
it's
can.
just,
I think you could do it. You want to do it there, or
yeah, just.
Okay.
Oh, you want to write over there?
I mean, you probably could write it like in the lower. I bet you could fit it in the lower corner of the front board.
Oh.
And if you use the purple, it'll be easier to see. Oh, that's the red marker.
This one, right?
Yeah. Make yourself comfortable.
I don't intend to write the low part of the boards. You just
If you want to write somewhere else, go for it. I mean, I'm just.
So
Pull up a chair and write.
so according to this isomorphism, I got just this thing. The usual one. If I replace A0 as A minus B, so it's A plus B, and A minus B.
So in this case,
Yeah, it's just the real part. There's no complex
I'm sorry,
part.
I meant H4.
Yeah, but I'm just demonstrating the.
I got you. You're proud of this. I understand. As you should be. Yes,
H4 is.
I got you.
We didn't do for H4, so I guess.
That's why I'm eager to see H4, because I don't know the formula for this one.
Okay, sure. So I should write.
Despite my many requests, a certain student who shall remain mostly unnamed.
So.
Easy, because let's be. How's that go? So that's. So you're setting j equal to. So you're like that's like setting j equal to 1.
Yeah.
And the next one's like setting j equal to -1.
Yep.
And then the next thing you write down.
Oh, it's I. So I got A plus BI plus CI squared plus DI cubed. Except this one is equal to I.
Right.
And then next one is.
But there shouldn't be a next one, right? I mean, that's it, right?
Oh, yeah. Yeah, I forgot. It's just I to the.
Oh, yeah, the product K equals 1 to 2 minus 1, which is 1. Oh, it's a kind of
just a
boring,
1.
kind of silly product.
So this
But-
one I
but-
can simplify into.
So I'm trying to visualize it here. K equals 1, n equals 2. So that cosine term is gone. And you're just basically setting j squared equals to -1 for the last thing, which is, for this case, just mapping j to I. And so that's your isomorphism.
There's weird stuff when you go either end.
So then,
I could do the square root thing here to
Go for it. Yeah, yeah. Complete your thought. Don't let me distract you. I wanted to understand that formula better,
Okay.
and I think I do that now. So
So
perfect.
using the note, using that
You
way.
can erase the purple if it's not helping you. I got it.
I mean, so using the weighted norm on this problem right here. Plus 2. I think it's a minus c squared. Yeah, b minus a squared. So,
what is this you're writing down?
the weighted norm on this side for the top of Riemann complex.
Oh, okay. So you're using this.
The weighted norm like AI equal to 1, B
Okay.
equal to 2.
So basically, this norm says that complex numbers are twice as important as real numbers.
I guess. I mean, complex number is like, yeah, I have
some sort of formula, some sort of mathematical reason.
I mean, complex number is overrated, I guess.
Ah. Spoken like a realist. See, now I'm going to have to edit this if we're not careful.
Oh my gosh. I just said. Okay, so the first.
For the record, I was not the instigator or the approver of said joke.
Oh.
Oh.
Okay, so the first two will be simplified into this one because I have minus b and minus d here. And the second one should just be a plus b squared plus c squared. B squared minus 2ac minus 2b. So we got 4.
The difference between you and me is I would have stayed down.
Yeah,
That was the rest of the lecture I would have done from that level.
I got lazy.
Okay, so
Yeah, should right.
so you got all your squares. So your point is you've got 2 squares.
Yeah, I should write into this.
Wait a minute, don't you have more? I mean, you got more squares to spare.
Yeah.
I think you could square spare. I think you've got.
I mean,
don't you have 4 a squareds, for example?
4a squared.
By my count, there's 1 a squared in the first.
Okay.
There's 1 a squared in the second, and then you've got 2 more of them in the bracket term. So wouldn't there be a total of 4 a squared?
Yeah.
Oh, but you do have. But you have got 2. Both. Okay, I see.
Yeah, I write here.
So you group 2 of them together. The 4ACBD.
Yeah, right. So it's
So
more.
you rearrange all these terms, and then what happens?
Rearrange the term.
You're. Yeah, go for it.
So.
We'll trust you.
So this is just like this is kind of something.
Oh, right.
So, yeah.
I see that. I see that. So the cross terms of a plus b and c plus d, you've got a plus 2 of them.
Yeah.
You've got a minus 2 of them. They're like
Cancel.
in.
So. Yeah. If I write the next one is just. Oh yeah, I forgot to.
Yeah.
So I got 2a squared plus b squared plus c squared plus d squared plus 2 plus 2. And yeah. The next term is just differs at 2a minus 2ac minus 2.
So let's see. At the moment, you're just working on what is the lopsided. Whatever you want to call this thing, the double complex norm on the right-hand side of your R2 cross C. and you come to this formula. So, what does that mean? Sorry.
If I cut this part, so it will be 4. A squared plus b squared plus c squared plus d squared. Right on this one.
So you actually have that it's equal. So it's 4 times a squared plus b squared plus c squared.
Yeah.
Which is to say that your k, in fact, is equal to 4.
It's actually equal to 2 because I squared them on.
Oh, sorry.
Yeah. So it's just k squared.
Okay, so n is equal to k squared,
Yeah.
interpreting back to the start.
Yeah.
So what does that then tell me?
So let's see.
Oh, but then you're going to tell me that you already know the submultiplicative constant for the weighted piece because you got that general result,
Yeah.
which you wrote for me in black in the upper left hand, right? Like, it's kind of this point on it. So you already know this, right?
Yeah.
Which means that you know this is less than or equal to, like, sorry, words.
This
Which is the A and which is the B in terms of the m sub A equals to kmb.
this.
Yeah, which is the
Yeah.
B.
I think A is equal to h2n and B is equal to r squared times c n squared. So I got.
So that arrow there, this arrow,
Yeah.
that's the phi.
Yeah, that's the B. So this one is weighted. It is equal to square root n times the norm on the hyperbolic number. And this one is related to B, and which multiplicative constant is 1. So this one related to it has some multiplicative constant square root n. It's got back.
Sorry.
Maybe I should write.
What's the concluding? So you get, sorry.
So this one has some multiplicative. And then we can retire MA is square root n times B.
Okay, that's not the before. And A is, there it is. Of course, you just showed us the details.
Yeah, that's summary of it. I mean, the important part is to prove this inequality, which is, well, take me a little bit of time.
So, how long did you work on this until you thought to make up this crazy lopsided norm for the Rm cross Cn?
Well, I work on.
Because without this very creative
Yeah.
and completely non-obvious idea,
Yeah.
I don't think you get this result, right?
Yeah, I work on to h5, and I see a part. Like the real part has just the constant 1, and then the complex part has a2. So I work to h5. So it's very crazy stuff.
Whoa, so what's this?
Oh, this one is for dual numbers.
Oh, for the dual numbers.
Yeah, these two I verified with the Lagrange multiplier, but this one is I just verified for like x equal to y in this.
Yeah.
And it's already very ugly. So I don't want to work on more.
Pretty.
Yeah, I mean, all the instant here we have inequality happens when x equal to y. But this part is happening when I think x equal to y. I should write
Oh.
equal to 1 plus j plus j
plus j. That's where you see it sharp. I'm familiar with that. But that continues to be cool. Oh, well. Thank you, Khang. You have increased the number of submultiplicative constants that I know precise values of by, well, as many as you have, since I only knew one before.
Yeah.
So if you found 10, countably many, oh, right.
Yeah, I guess
The countable increase, that's not too shabby.
I mean,
Thank you.
once you find the isomorphism and a little bit of hot water to risk quality.
Yeah, excellent. Thank you for showing us this. So I figured that's about a 90 for Khang's homework. That's setting the bar for you guys. So,
It
yeah.
was just a joke when I say prove the square root of everything.
So I'm guessing that the analog of this for the nth order case is quite horrible, huh?
I know the case.
I mean, this calculation you showed us for
Yeah.
n equals to 2,
Yeah.
but you convinced yourself it's true for arbitrary n. Do you have like an induction proof, or?
No, I use a little bit of equality here.
Or is it more based on these formulas up here?
Yeah, it's about the e to the
Okay,
side.
okay.
So, so I would say
Oh, beautiful.
So-
Yeah.
So-
Have you guys ever seen this? So what that is if you look at the unit, if you look at the group of units around the, here's 6. If you add them all up, where's their geometric center? 0, right. So the center of mass of the group of units, if you will, is 0. That's what that is. So that's the foundation for the. All right. Okay, so let me continue to tell you guys more calculus. Then I'm going to turn the page here. I'd still like to say more about complex number. Yes. The Lorentz hyperbolic numbers and Lorentz transformations. But let me save that for some hypothetical future day, since I'm not currently up to speed. Who wants mission 2? Oh, who? You do. It's linear. Exciting linear. I hate to erase these things, but yeah.
it's eternal.
Okay. Well, now that we're done with the discussion, I will. Oh no.
Just that to say that from the one who writes on the board. So. In a Word document?
A Word document. That seems like fighting words. All right. There we go. If I left the mic at 60 and then put it on my lapel, the rest of the lecture would be deafening. The stupid clippy thing has come off my, it's got this thing that pops in the back, but for the life of me, I can't figure out how you actually, I've forgotten how it actually pops in. It's not entirely obvious, and oh well, fortunately I have pockets. So I've been told by the students that I should actually get a new mic so that they could listen in both ears, but oh well, not going to happen. I mean, if some rich benefactor wants to send me a brand spanking new Sensenheimer or whatever that thing is. They're one of them fancy schmancy $600 stereo broadcast quality mics. I'd be happy to start using it in my classes, but short of me or my wife getting a raise, don't see it happen. Oh no, that's they can, if they hear that they should give us a raise. I don't want to edit that out. No. Okay, so one of the problems that you eventually come to as you study calculus, of course, is integration, right? And so we've been pretty successful in studying integration over an algebra, and I just want to share with you some of our main results, the definition and so forth. Yeah. So here it is. So to start with, I suppose I have a function which goes from, say, a closed interval to the algebra. And again, I think in this we're going to assume that this is commutative. Although I do think, I have not, it's not because I have a smoking gun that says, oh, if it's non-commutative, it doesn't make sense. It's not that. It's just that I haven't fleshed out what the nuances of the non-commutative case would be and why it would be interesting. So I just assume commutative since I'm not thinking about it. So a commutative, commutative algebra. And by algebra, of course, I mean associative, over the reals, finite dimension, unital. And we'll suppose beta, v1, v2, vn, basis for A. And we'll have component functions. So f will be equal to, say, u1 v1 plus u2 v2 plus plus un vn. So here, the u sub j are what? These are real valued functions of a real variable. Okay? So just garden variety, real valued functions of real variable. And then, well, the definition of the integral from a to b of f dt is just like we do in calculus 3. We just integrate component by component. Okay, so that's the starting gambit, so to speak. All right. The properties of that are as expected. So first of all, you have linearity, right? And so part of the place I got this idea was I've studied complex analysis out of Gamelin, and so he I think if I remember right, he actually starts by doing these kinds of integrals and then uses them to sort of bootstrap his way up from these to complex versions of like Green's theorem. So there are like natural complex versions of Green's theorems and so forth that you would never think about in calculus 3, but they're really not especially complicated if you just were willing to work with complex valued integrals like this, right? So what are the properties? One, the integral of f plus g dt is, as you'd expect, the integral of f of d plus the integral of g dt from a to b. All right, not especially surprising. This one's a little bit new. If we have the integral of a constant, times f in the algebra, right? Well, then we can pull that constant algebra multiplication out of the integral like that. In the case of a complex, in the complex case, this is also true and interesting. What's the proof of that look like? So essentially this, if I have alpha times f, that's equal to the sum over k of ci j k alpha I uj vk. Using the structure constants like usual, that's the formula. And so the kth component, this is the kth component function of, alpha times f. So when we integrate alpha times f from a to b over t, well, by definition, that's the sum k equals 1 to n of the integral of cijk alpha I uj dt vk. But then there's structure constants, so we can pull those out. And alpha sub I, that's the ith component of alpha, there's also a constant, it pulls out. And we got, we've got sum over k, right, of c I j k alpha I, and then integral of uj dt from a to b, right? Yeah, and then a k vk. But of course, what's this? This is nothing more than the integral of f dt from a to b. It's the jth component of that. So then by the definition of structure constants, that's precisely alpha times that integral. And then property 3, which is probably even more exciting, says that the integral from a to b of df, big F, dt dt is, you guessed it, big F of b minus big F of a. So there is a fundamental theorem of calculus part 2 for such integration, right? And what do we mean by df dt? Here, df dt is equal to the sum, right, I equals 1 to n of d fi dt vi, right? It's the component-wise derivative of f. Okay. Which is not at odds with the Fréchet derivative definition of derivative, and this being the Jacobian matrix of it, blah, blah, blah. So how do you prove 3? Well, write the definition, and then just apply the fundamental theorem of calculus to each component one at a time, regroup things, done. Okay. Curious. Is there something in here next? Is there something in here, or are you guys just taking out? Oh, okay, that's cool. No problem. Just checking. What's that? They're waiting for physics class. So exciting stuff. Well, I think across the way. So, all right. So, getting to the point, guys. So I say, okay, well then, the definition I'm actually interested in, right, is if we have f. So suppose it's a function on some subset of the algebra to the algebra again, where I, includes rectifiable curve C from P to Q. So rectifiable means that you can rectify it. It means that you can chop it up into polygonal approximations, which in the limit converge to the curve so that the following makes sense. Something like that anyway. I'm not an expert in integration, so I could be butchering some nuance there. But the basic idea, though, is here's P, here's Q, right? And maybe this is the curve. So you're perhaps approximating it with some broken line segments that go from one to the other. And anyway, we define the integral over C of f of zeta. Zeta, my nemesis. Zeta. This is the algebra integral. F of zeta d zeta is going to be the limit as m goes to infinity of the sum I equals 1 to m of f of zeta I star delta zeta I, right? Where this delta zeta I is equal to zeta I minus zeta I plus 1. So like here is, I suppose, zeta 1 in my picture. This is going to be my zeta 2. Takes me entirely too much time to think about how to write a zeta. This would be my zeta 3. And so like m is equal to 4 in my silly picture. But we take the limit as m goes to infinity. That gives us the notion here. You should recognize this. This is exactly, if you collapse it down to the reals, this is the Riemann integral, right? But this is sort of the natural abstraction of the Riemann integral. This definitely makes sense for complex numbers. And this will give you the complex integral that you study in complex analysis. And so, a direct theorem that follows from this definition, it's pretty easy, is that the integral of C of f of zeta d zeta, right? I cannot draw zetas for the life of me. F of zeta, why didn't I choose a different letter? I mean, I'm trying to play nice with others. F of zeta d zeta less than or equal to m sub a, big M, L. So here, where I'm assuming that the norm of f of zeta is less than or equal to m, the length of the curve C is equal to L, and of course the norm of x times y is less than or equal to the submultiplicative constant times the norm of x, norm of y, which we had a master class in at the start of today, right? So I sometimes refer to this as the Ml Theorem for the stupidest of reasons. But yeah, this is the often referred to in complex analysis as the Ml Theorem, because in complex you get multiplicative of the norm, right? And so you bound your complex function, you take that bound, multiply it by the length of the curve, and that gives you an upper bound on the value of the complex integral, the modulus of the complex integral. This is completely easy. The proof is absolutely trivial if we adopt the definition that I just did, right? All you do is take the norm of this thing, apply the definition of m sub a, right? And then you replace that with its bound, you pull the m out, then you're left with an integral which represents arc length, and so out pops this result. The explicit steps are in my paper, but the proof is entirely natural. The proof that you might have seen in your complex course might not resemble this at all. Because in the case of complex analysis, there's another argument which can be given in terms of polar form to derive this estimate, which would not look anything like this. Is a totally natural result from that definition. But this definition also can be can be restated, it can be reformulated in terms of parametrized curves, right? So how do you, oh, it, sorry, what? Oh, okay. I know we're all still just coming down off the excitement of having the Bachelor and his prize from that whatever season it was. So, yeah, I know, exciting stuff. For us, this is a theorem, but you could take this as the definition. So if zeta, from T naught, good grief, T naught comma T1 to the curve, that rectifiable curve we're talking about, is a differentiable, parameterization. So technically speaking, for complex, we look at arcs, which are built from parametrized curves strung together with finitely many crooked points or corner points, right? I mean, that notion of an arc, it's nastier than parametrized curve. I mean, I'm assuming that we have a smooth parameterization overall as C, but clearly the concept that you actually want to do problems with is where you at least only have parameterization of so much, right? Like this much, and then there's a corner, and then you got to parameterize this part, and then you got to parameterize that part, and then you got to parameterize. So there's like 4 different smooth curves, and so there's a lengthier definition where I say to calculate the bit lengthier theorem where I say to integrate over something like that. You take the sum of the integral of the integrals over each piece, like I'm about to write down. You guys know this. Anyway, long story short, integral over so the C I'm thinking about is just like that, okay? Integral over C of f of zeta d zeta. It's equal to just what you'd expect, integral from T naught. I got a TF. Here's a typo right here. I got to fix that. I got a T. I should have T1 here, or I should have TF here. I've got a TF in the integral, and I got T1 in my domain for zeta. To quote my community college professor, that dog's not going to hunt. I'm sorry, he wouldn't say that dog's not going to hunt. He would just say the dog's not going to hunt. It's here. It's not quite accurate rendition of my community college professor. But that might be a somewhat accurate rendition of one of the students in the class that I was with, if you could get him to say it for him. So anyway. Oh, Crazy Paul was not at my community college. I'm not. That's an interesting thought experiment for me. How would a Crazy Paul have interacted with my community college friends? I think they would have gotten along just fine. I mean, there would have been some arguments about certain things, for sure. I'm not sure I entirely understand what those arguments would have been, though. It's really kind of unexplored intersection theory for me. I don't know. You've raised an interesting question. I don't know how to answer that.
What classes was this that you took for your community college professor?
Community college, I had like electronics, so DC, AC, troubleshooting, circuits, college algebra-based physics for a year.
You know when you said carried around the broken end wires?
Oh yeah, he'd make us leave the room, and then he'd have his own bucket of broken. He used to walk around taking wires and just going. His goal was to break the wire inside the insulation. That's what you need for troubleshooting class. Then you just take a wire out and you put that in after the student's out of the room, and then us finding that is troubleshooting. I mean, that's part of troubleshooting. It's not all, but it was fun. It's fun. Oh, okay, anyway, so this, you know, this is just the natural, and so, you know, for example, you know, complex, right? So you look at u plus u plus iv, right? And the d zeta, right? So that times, well, let's say dx dt plus I times dy dt, right? So this would be my quote unquote d zeta dt, you know, and this would be my f of z of t. I just haven't written the z of t dependence, right? And you integrate over your parameter domain, whatever that happens to be. And what do you get? Well, you get integral from t0 to t1, you know, of u dx dt minus v dy dt plus I times the integral from t0 to t1 of v dx dt plus u dy dt. And so, you know, we introduced notation in Calculus 3, which says we can just write these as integrals of differential forms, essentially, right? Like this is, by definition, the integral over the curve of u dx minus v dy, and then plus I times the integral over the curve of v dx plus u dy. And that's the complex integral. But, you know, from a purely formal perspective, that's really just c times u plus iv times dx plus I dy, you know, in the most natural way that you could think of. And so if you want to write down the hyperbolic integral, you just change the I to a j, and it does everything the same except puts a minus. That minus becomes a plus, but that's the hyperbolic integral. And so I start to think of d zeta as a thing on its own. I think about the differential of the algebra variable as its sort of own thing. And for me, I start thinking of d zeta as something like, you know, dx1 plus v1 dx2 plus da 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 plus vn dxn, provided what? Beta v1 has coordinates what? x1 through xn, and what else? What am I assuming about the first thing in the basis? Yeah, it's the identity, which is why I didn't write v1 here, you know. Of course, you could put v1 there, and then that would be, if I don't have a special place in my heart for one of the basis elements, then I just put a v1 there, and that would be my d zeta, if you want to think about it. You could kind of think about it having its own independent sort of existence, in the same sense that I think about, you know, ds vector or dr vector or other things like that in Calculus 3 having their own sort of at least symbolic existence. Whether or not that's good mathematics, I don't much care. It's good heuristics. Theorem, I mean, I care. 10.7, otherwise I wouldn't have said that. Theorem 10.7, and we've talked about this before, but I'll say it again. The derivative of f of zeta of t is equal to what? Well, it's equal to f prime of zeta of t times d zeta dt. Oh, this is supposed to be 2. Thank you. Yeah. Thank you. So this is the chain rule, and this chain rule is really behind why so many of the theorems of integral calculus generalize to the complex integral. And you'll see this proved on the basis of Cauchy-Riemann equations in a complex course, but it's really got nothing to do with that. It's more about this general chain rule between an algebra. And anyway, I have a proof of that on page 47. I won't go through at the moment. Maybe I will. Actually, it's probably healthy for us to do that. Let me look at the proof of this right quick. So d dt of f of zeta of t, right? So by the ordinary garden variety chain rule of multivariate calculus, so f is a function from a to a, right? So you can think of a having variables, Cartesian variables, normed linear space variables of x1 through xn. So the plain old garden variety chain rule says, well, it's not entirely plain. It's the, let's say the advanced calculus chain rule, if you will. I equals 1 to n, partial f, partial xi. Now, if a was actually equal to Rn, then this would be straight up be calculus 3, written in a different notation. But I'm not actually saying that a has to be Rn today. So, you know, let's be a little bit more open-minded. Maybe that. All right. But then I'm assuming that f is a differentiable function. So that means it applies the Cauchy-Riemann equations, which means that I can trade this guy for what? How about partial f, partial x1? Right? Evaluated at z of t times what? Times vi. But then this is, I can just pull that out of the sum by properties of sums and so forth, and the algebra, and what do I got? What's the sum over I of vi dxi? Well, that's exactly d zeta. If I could make a zeta once in my life. It's painful. So you can tell me that, and it'll write sometimes I make them so beautifully, and then it just all comes apart somehow. So, but there it is. My point was, it's not because of the complex Cauchy-Riemann equations specifically. You have to use the complex Cauchy-Riemann equations to derive this in the complex context. But it's not a complex thing. It's a calculus thing, this chain rule. Is my larger point. And that's important because it means that we can then prove this integral, that f of zeta d zeta is equal to f of q minus f of p, given that what? F has primitive, right? And here this C goes from P to Q, and I'm assuming, of course, that the big F exists all along C, and probably I need to have it near it too. The proof, here's the proof. So we integrate along the curve. Now, of course, if the curve was not, you know, parameterized by a single parameterization, if it was actually an arc, then we'd have to break, you know, we'd have to take a sum of these results, and the intermediate steps would cancel out, and we'd just be left with the terminal points at the end of the whole thing. So, I mean, I'm doing the proof for a parameterized curve, but of course it's easily adapted to an arc.